Hi guys! I wanted to talk about the mean value theorem, but before I did that I had to talk about roles because it kind of precedes it and it's pretty important, and you know that since you read your calculus book, and I shouldn't have to explain that to you. So there's a few things about roles that I really think are important, and we're going to go over that, and then next time I'm going to do the mean value theorem because that's what I want to do ultimately. Anyway, so Rolle's theorem says let f be differentiable on the open interval ab and continuous on the closed interval ab. Then f of a, if f of a is equal to f of b, there's at least one point c in the open interval ab where the derivative f prime of c is equal to 0. So there's three conditions, and we're going to talk about all of them, and they're really important, I think. So I'm going to try to make this quick. Rolle's theorem is about functions and how they behave. This means that Rolle's theorem tells us something about how the function works as it moves from start to finish. So as it moves from left to right, it changes, which makes sense. This is calculus. So we have three constraints. F is differentiable on the open interval ab. F is continuous on the closed interval ab. And if f of a is equal to f of b, then there exists at least one point c in ab where f prime of c is equal to 0. So these two are going to carry over into our mean value theorem. We should remember that. And this part right here is kind of, it's a Rolle's only type of deal. So this part right here is Rolle's and Rolle's alone. And something to say about Rolle, he's from France, and he hated calculus. He didn't actually put this theorem together in support of calculus at all. He argued his entire life practically, or his entire adult life, that calculus was crap and that limits were ridiculous. So this was actually put together by an Italian mathematician, Bellavista, in 1846 after he died from his notes. So that's pretty interesting. The constraints, though, serve two purposes. Alright, the constraints pick out one class of functions from all the other functions, and only the continuous ones. So, everything else, no. Continuous functions only. And then, constraint number 2 picks out one class of processes for these functions that we picked out. Moving on. In other words, the constraints demand that the function have the fundamental properties of continuity and differentiability. So that should sound pretty familiar. So going over constraint number 1, what does it mean to be differentiable on an open interval? And suppose we have a parabola, just a nice little basic parabola like this. So we have f of x is equal to negative x squared plus 2. Why is my camera kind of weird? Whatever. Alright. So if we were to take the derivative of every point on the graph here, alright, we'd have a linear function, and that would be continuous too, right? Because we have a polynomial, and a polynomial derives into a linear, and those are both continuous. So our continuous function gives us another continuous function, and that is also differentiable. So if f is differentiable over its entire domain, which is all reals, because it's a polynomial, then of course it is differentiable on a restricted domain from a to b. And this is an open interval, so it does not contain its endpoints. So it does not contain a, and it does not contain b. So this part basically says that when f is differentiable on the open interval ab, the function of f's derivatives within a to b all exist. So between a and b, f is differentiable. Okay? So I really want to know why that's doing that. So what we have is constraint number 2, and what does that mean to be continuous on the closed interval ab? Well, continuous just means uninterrupted. Alright? So closed interval includes its endpoints. That's also a thing you need to know. So we have a function right here, and we can see that it's smooth. Alright, just pretend this is a perfect function. Pretend. Alright, so we have, if we change our x, if we move this way just a tiny little bit to maybe our next little x, then our y isn't going to be much different than our last y. It's going to be a little bit further over, right? So maybe that's better. That is not better. So it's just going to be a little further over. It's not going to be up here. Our next y isn't going to be all the way up here. It's not going to be all the way down here. It's just going to be a little bit further over. Alright, so it's smooth. There's no big gaps. Nothing's going to happen to it. It's just a nice, smoothish function. Alright, moving on. Constraint number 3, which is the rolls kind of deal, says that f of a is equal to f of b, and these are equal to 0. So when our input's a and our input's b, we have the same output. Alright, same output. In this little graph here. Ooh, I shook it, sorry. Alright, so this is what you want to kind of understand about this. Alright, so we have our left endpoint, we have our right endpoint in our interval, alright? These are inside. We're going to continue this closed. Alright, so this means that this is an absolute maximum right here. So it never gets any higher than this, and it never gets any lower than these. We are only concerned with A, B, and between A and B. We don't care about what it might do in any direction for infinity. We just care about that. So right here we see this is just a straight line. This is our axis, or x-axis. It's also y equals 0. So if we were to take our derivative of this line right here, y equals 0, then it's every single point on this line is going to have a derivative of 0 as well. And that makes perfect sense. So if b is our derivative of any straight line like this or like this, then x times c, which is 0 in our case, is also 0. So the derivative along this line is 0, 0, 0, 0, 0, 0, and nothing ever changes. Okay, this is important. Up until now, our derivatives have been, they look dependent on our function. We derive them from our function. But in the case of a line like this one, we see that no matter what x we put in, no matter what change we order to the function, our independent x, no matter what independent x we put in there, it's just going to get multiplied by 0. And it's just going to be 0 again. So no change can ever occur. The derivative won't allow it. And the derivative is the 0. So the derivative allows no change to occur on a straight line, which you really want to think about that. This means that the derivative isn't as dependent as it seems. Right. And we're kind of going to go into that later with the mean value theorem, but what I want you to notice here is that here at the maximum, what we have is a tangent going right through it. And we'll notice that this derivative here, this straight, well, it's not a derivative, this line right here is parallel, exactly parallel to this line. And since they're parallel, they have the same slope. Alright, so this says when these two are equal, this and this are going to have the same slope. So for this, I don't want to call it a chord yet. Don't call it a chord yet. From this area here is going to be exactly parallel to this area, this tangent right here. And you need to remember that. Oh, I gotta wrap this up. This video is going to be too long again. Alright, so here we have a function, a to b, f. Here we go. In some sense, this is Berlinski. Something about the curve is controlled by the fact that a and b have the same value. Rolle says that a change in the behavior of a continuous curve is tied to a number, and Rolle achieves, it reveals a connection between the property of continuity, the fact that change exists and it occurred as x moved between a and b, and the existence of a particular number. Alright, so Rolle says a number exists, yay, but it doesn't tell you what it is. Alright? And then it says, well, we want to say that at a point where a curve changes direction, the line tangent to the curve must be parallel to the axis. And Rolle says this. That's what I was trying to explain back there, but I don't have words. So that's our change in behavior. This point right here is our change in behavior. So just one more thing real quick. Oh no, I'm going to go over.